So 75. So we're trying to find the GCD, the greatest common divisor for 45 and 75. Greatest common divisor or factor, GCF, same thing, like from your algebra days, factoring. The way I'm doing it is I went over here and I took the 45 and I broke it down to its primes, and then I made the little tables that we just learned how to make, and I listed all the things that go into 45. Now let me do the same thing for 75. 3/4 is 75 cents, and then 5 times 5. So 75 is 3 times 5 squared, isn't it? That's the guts, the DNA. So let me make a little, start with 1, times 5, times 5, times 3. You with me? Times 1, times 5, times 5, times 25. There we go. There's all the numbers that go into 75. So 75, I'm going to list them from smallest to biggest. 1, 3, 5, 15, 1, 3, 5, 15, 25, 75. There's all the numbers that go evenly into 75. So those are the factors, right? The divisors. Right? We got all the things that go into 45, all the things that go into 75. Now, what do they have in common? What are their common, right? Because that's what we're trying to find here. Common divisors or factors. They both have 1. They both have 3. What else? Both have 5. Anything else? Both have 15. Those are their common factors. Common divisors. So what is the greatest among the common factors? 15. So the GCF is 15. Or GCD, same thing. Either way you want to say it. GCF, GCD, it's 15. The greatest number that goes into both of those, the biggest number that divides evenly into 45 and 75 is 15. You might have known that like a long time ago before we did all this work, which is fine. But here I'm showing what's called the intersection of sets method. What do I mean? Well, I listed the collection. Set just means collection. Like we're a set. We're a collection of people, right? So this is a set, a collection of numbers that go into 45. Here's a collection of numbers that go into 75. Among those two sets, we took the intersection, right? We took the numbers that were in both lists, right? Boom, 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 and boom. Those numbers were in both lists. That was the intersection of the two sets, and we took the greatest. That's called intersection of sets method. Good there? We'll try one of those. 45 and 36. So try the same thing. So list out everything that goes into a 45. List out everything that goes into a 36. And then take the intersection of the sets. Find out what's in both lists. 1, 3, 5, 9, 15, 49. So we've already got the 45 done. We did it a minute ago. And we did 36 actually a couple minutes ago as well, didn't we? 36, 6 times 6, 2 times 3, 2 times 3. So 36 is 2 squared times 3 squared. So 36 is 2 squared times 3 squared. So if you do a little thing for the 36, times 2 times 2 times 3 times 3, just like we did a minute ago. Find all the factors, divisors, times 1, times 2, times 4. List them out. So for 36, it's 1, 2. You don't have to put them, you can do them in whatever order you want. It might be easier if you go lowest to highest. It doesn't really matter a lot. I just blew it. I forgot the 9. I'm blowing it. I'm just going to list them straight, not in order, because I might mess up. All right, so there they all are, 4, 12, 36. What do they have in common? What's the intersection of those two sets? What do they both have? Looks like they both have 1. That's always the case, huh? 1 goes into every number. They both have 3. They both have 9. What's that? Sorry, I can't hear you, Jose. What was that?
I think it's 9.
Yeah, I think so too. There's nothing else, right? Am I missing anything? I don't think so. Yeah, so it looks like 9. 9 is the greatest factor that they have in common. So I listed the common factors, 1, 3, and 9, the greatest one being 9. That good? Is that making sense? Intersection of sets? Now, we're going to do the same thing for LCM. So, let's do that. So, going back to number 1 again. So now the LCM of, what was it, 45 and 75. Okay, now what does LCM stand for? Least common multiple, yeah. And it's the same thing as if you did denominator. You know, LCD, same thing. It's exactly what you do when you find common denominator for two fractions. That's what this is getting kids ready to do as they move into the algebra years. They'll know how to do LCM. So, how do you do least common? Well, what is a multiple? Let me write that out for you. The multiples of a number are times 1, times 2, times 3, times 4, etc. Just multiplied by 1, 2, 3, 4, etc. So if I take the 45, first thing I'm going to do, I'm going to list his multiples. So it's going to be 45 times 1. That's just 45. Then it's going to be 45 times 2. It's going to be 90. You can definitely use your calculator for this. 45 times 3, 135, I think. 45 times 4, 180. 45 times 5, 225, I think. Is that right? Yeah, I think that's right. Anyway, how far do you go? They go forever. I don't know. That's pretty good. Let's just do that. And then come on down. Now let's do it for the 75. Let's list the multiples of 75. 75 times 1, times 2, times 3, times 4 would be 300, times 5, etc. They go forever as well. Are we good so far? So I'm listing the multiples of the numbers, which means just times 1, times 2, times 3, etc. And what am I trying to find? The least one they have in common. The lowest one they have in common. Do you see it? What's the only one they have in common up there? 225. Now they would have another one if you kept going. I don't want to keep going. But if you kept going, I think it'd be like 450. They would have that one in common as well. And, well, they'd have infinite forever. But the lowest, among their multiples, the lowest one they have in common is 225. So what that means is if I was doing fractions, if I was adding 145th and 175th, I wanted a common denominator, it'd be 225. That'd be the LCD. That's the least common denominator. What that is that's the lowest number that they both go into. That's bigger than them that they divide into. So you see how GCD and LCM are exactly the opposites? So we're doing LCM, we're finding the lowest among big numbers. The lowest number, right? Because 45 goes in there, right? It's right here in the list. It's 45 times 1, 2, 3, 4, 5. 45 goes in there 5 times. And 75 goes in there because there it is in the list. 1, 2, 3. 75 goes in there 3 times, doesn't it? So both of them, it's like a container. How about that? That's how I think about it. An LCM is like a container that holds both 45 and 75 in it. You could fit 5 45s in there perfectly and 3 75s in there perfectly. It's the smallest container, least, that you could use that would hold either one, or not both at the same time. That's why I hesitate to say both. It's not both at the same time, but it's both evenly, one at a time. It's the smallest container they both fit into, one at a time evenly. Yeah?
I learned a pretty easy way to do it because later on we start adding another number, so it starts getting a little complicated.
Yeah, I'll show you some other techniques.
Okay.
Yeah, but I will ask, because not only answers, but there's also concepts. So, because with teaching kids, part of the deal is the concepts, not just the answers. Yes, I'll show, it's a good question. I will show like a slicker, quicker way, maybe some of you already know it, to get some fast answers. There's a method called the ladder method, which is the best for getting LCM, way easier than this crazy thing. But the concept is important. Why? Why? If there's a better way to get the answer, why do we need the concept? Well, because higher math, it's letters. It's not numbers at all. All of a sudden it's X's and expressions and science and math, engineering. It becomes letters, and then it's all about the concept. Number techniques do nothing for you at that point. If you never got the concept and just learn number games, you're sunk. And you don't want to do that for kids, right? You want to lay a foundation in all the math you teach for them of getting the idea, because it's the idea that really plays out. Calculators can run numbers for us, right? And computers are great at that. But we still need to understand concepts in order to tell the computer what to do. Anyway, yeah, good question. We will get both. So on the test, I want to be real clear with you, and I'll remind you next week on review day, Monday. But on the test, I will ask you to list certain techniques. So I'll say, show me the LCM by the intersection of set values. So I'll want to actually see this method, because that gives a concept. That gives the idea that these are multiples on this. Shall we try? I think you got that. Let me go on to that's number 2, isn't it? So number 2. I think this one I called number 2. It was actually 1B or something, wasn't it? Anyway, number 2, which I already forgot. Let me see, is it here? Yeah, number 2, 60 and 2200. Okay, so number 2, find the GCD of 60 and 2200 by prime factor. I'm going to run out of room on that word. I'm going to abbreviate it. By prime factoring. By prime factoring. So, this is a different method. I'm not going to list the sets. I'm not going to make that big array. It starts the same as the last method. You got to take the 60 and you got to break it down to primes. And then you got to take the 2200 and break it down to primes. So here we go. 6 times 10, 2 times 3, 2 times 5. So what's the guts? What's the DNA of a 60? 2 squared times 3 times 5. And then let's take the 2200. What's the easiest thing to do when numbers end with zeros like that? Times 10 or 100 or something like that. So 22 times 100. Right, that's what puts those 2 zeros at the back, huh? We good there? And then break down the 22, 2 times 11. Break down the 100, 10 times 10, and each of those 10s, 2, 5, 2, 5. All right, so we got 1, 2, 3 2s. 2 to the third, 2 5s, 5 squared times 11. There's the guts of a 2200, and here's the guts of a 60. Good so far? Kind of starts out the same. Primes are everything. And when it comes to number theory, primes are everything. All the methods start with the primes. Now, what do we do with these? We'll take the 60. Let me write it again right here. I'm going to kind of line them up all organized. And then I'm going to bring the 2200 down. And I'm going to put 2 to the third times 5 to the 6th. See how I lined up the 5s? Times 11. So line them up vertically. I wrote the 60 and the 2200. I wrote the prime. See, I left a space for the 3. I put the 5s over the 5s. I left a space with the 11. Like that. You line them up vertically. And then we're going to form the GCD. In fact, let's do the GCD and the LCM both. So the GCD or GCF, same thing. What's it going to be? Think with me for a second. Divisors, factors, are little things that fit into these numbers. I want something smaller than 60 and 2200. Something smaller that goes into them. And then the LCM is the opposite. The LCM is bigger than them, and they fit into it. See how they're reverse of each other? So factors are little things that go into a number. So right now I'm finding the greatest among the common divisors or factors. I'm just trying to say, what's the biggest number that'll fit into both of them? It's going to be smaller than them, but it's the biggest. It's the biggest number that'll go into both of them. How are you going to find it? Well, if you want a number that goes into both, you know what it's like? How about this? It's like if I said, what's the most they have in common? What's the most they have in common? What if like Jose? What if I said, Jose, how many quarters do you got in your pocket? And then I pulled out, I have no quarters, Jose, but let's pretend you had 5 quarters and I had 2 quarters. And we wanted to find out what's the most quarters Jose and I have in common. I'd say, Jose, you got at least one quarter? Remember, he's got 5, I got 2. Do you have at least one? He'd go, yep, I got at least one. So we have at least one cup. Do you have at least 2? And he goes, yep, I got at least 2. And I've got 2. And I say, Jose, do you have at least 3? And he goes, yep. I go, well, I've already actually done. My max was 2. So what's the most we have in common? 2. So it's the lower of the 2. Did you catch that? It sounds counterintuitive at first. The greatest amount in common is actually the lower of the 2 numbers, isn't it? But that's true, isn't it? Even though it might sound funny at first, it's the truth, isn't it? If you have 2, if you have 5 quarters, and I have 2 quarters, the most we have in common is 2, the lower number. So that's what we're going to do here. We're trying to find the greatest amount they have in common. So when it comes to 2s, what's the greatest amount they have in common? Well, 2 2s. They don't both have 3 2s. And you don't want to just say 1 2. They have more than that in common. They have 2 2s. Okay, when it comes to 3s, what's the greatest amount they have in common? None. They don't have any in common. The 2200 doesn't have any 3s. When it comes to 5s, what's the greatest amount they have in common? A single 5. And when it comes to 11s, what's the greatest amount they have in common? None. Multiply that together. 4 times 5, 20. 20 is the biggest number that divides evenly into 60 and into 2200. Everybody see what I did there? So basically, just to make it simple, you just pick, well, I'm kind of running out of room here. Let me rewrite it and do it so I really want to make it clear for you. So 60 again, so what was the 60? Let's do it one more time just to write out what I did. 2 squared, 3, 5. So that was 2 squared, 3, 5. And that was 2 cubed, 5 squared, 11. 2 cubed, 5 squared, 11. And then the GCD or GCF, same thing. You take, well, I don't know where to put it. You take the lowest of each power. So what's the lowest there? 2 squared. What's the lowest, even with 3s? What's the lowest 3? No 3s. So I take none. What's the lowest among the 5s? Regular 5. What's the most among the 11s? No 11s. Multiply that together. 4 times 5, 20. Good? Because that's what they have in common. That's the biggest number they have in common. Like with me and Jose. The most quarters we had in common was 2. Now, at the same time, let's come down and do the LCM. What are we going to do for the LCM? Now remember what the LCM is. It's a bigger container than them, right? It's bigger than they are. It's a number bigger than 60 and bigger than 2,200. A bigger number that they go into. It's the opposite. Instead of finding a little number that goes into them, which is GCF, the greatest among the little numbers, I'm finding the lowest among the big numbers now. The lowest among the big containers that they can go into. How do you do it? Well, what if I said Jose and I again? Let's do the Jose and I thing again. Jose's got 5 quarters, I've got 2. What container could we make that would hold Jose's quarters or my quarters? Not both at the same time. Not both at the same time. Jose's quarters or my quarters. How many quarters would it have to hold? 5. Jose had 5, I had 2. So not 7, but 5. Remember, it's not at the same time. We're not putting them in there at the same time. We want a container that either one could go into. Right? So the smallest, the lowest common container. The lowest container that could hold his or mine, not both at the same time, would be one of 5 quarters. It's the bigger number, isn't it? Instead of the small. That's the container that can hold either one. That's what we're doing. So what's the container? Let's just go through it again. When it comes to 2s, how many 2s would it have to be able to hold if it was going to hold either one? The higher power. When it comes to 3s, how many slots for 3s would it have to hold either one? A single one. The higher. One is more than none. When it comes to 5s, you just take the higher one. When it comes to 11, you take the higher one. Multiply that together. I have no idea what that is. Somebody have a calculator? Some big number. 6,600? Thank you. 6,600. That's a container that can hold either one. Not both at the same time. But either 2200 can fit in there or 60 can fit in there. That's the lowest container, right? Get the idea about the lowest? See, I could have got for Jose, and I could have got a container that holds 50 quarters. That would hold Jose's or mine, but that's not the smallest. That's not the lowest. Neither is 7. 7 would have held both of ours at the same time. That's not what we're talking about. Either one, Jose's or mine, right? So that's what an LCM is. It's a number that contains either one. So what do we do for that? We take the highest. See how it's exactly the opposite? This was lowest. The highest of each power. Take the highest. This took the lowest of each power. See the prime factorization method? You just break them down to primes. For the GCF, you take the lowest. And it's kind of funny. It's kind of counterintuitive, isn't it? For the greatest, you take the lowest. And for the lowest, you take the highest. But we already talked it out. It is true. For the primes in each slot. It's a little quicker than the intersection of sets, isn't it? A little bit faster. But both are important concepts. Both are important. Because the intersection of sets really shows the idea of a list of different numbers, you know. It really gives that feel, which is important as well. The concept and the method. I'm still not to the best way. There's even a quicker way to just snap out those answers. We're not going to have time for it today. But is that good? You want to try one of these? Why don't we try one with our last? Try 45 and 36. Go ahead and do the prime factorization method. This is a long section. I plan to be on this like, for sure, all day Wednesday as well. Yeah, that's the schedule. So we'll be on this all day Wednesday. Today, all day Wednesday. So find the prime factors. So break those down. We already broke those down, didn't we? Let me just do that quick. What was 45? 5 times 9, so it was 3 squared times 5, right? And 36. Remember, you want to line things up, right? Same primes under same primes. So leave a little bit of room. 36 was 2 squared, 3 squared, I think, right? Okay, so come underneath and do the GCF, and then below that, the LCM. How we doing? So with GCF, it says greatest common factor, but you actually want to take the lowest of each power, huh? Because that is the greatest amount they have in common. Like Jose and I, 5 quarters, he has 2. If I have 2, he has 5. We have in common 2. Common means the lower amount. So when it comes to 2s, what's the lower amount? None. Right? The 45 has none. So that's the lower amount. We take none of those. When it comes to 3s, it's just 3 squared. They're the same. When it comes to 5s, what's the lower amount? None. Again. So that's it. GCF is just 9, which we already found back over here, didn't we? Somewhere. There. Yeah, 9. 9 was the GCF. This way was harder, huh? Intersection of sets, right? Let's go back to this LCM. Now, LCM, you take the highest. Because it's a bigger container that either one of them separately fits into. Not both at the same time. It's that you take the highest of each power. So when it comes to 2s, what's the highest amount I see? Well, 2 squared. When it comes to 3s, what's the highest amount? Well, 3 squared. When it comes to 5, what's the highest amount? Just a plain old 5. 20, is it 180? Do we do that one already? Maybe we didn't do that one. No, I made one up. Yeah. 180. 20 times 9. Yeah, 180. 180. Is that making sense? On that. I took the highest of each power because it's bigger than them, right? It's got to be able to contain either one of them. On that. All right. So we're just getting going on LCM and GCD.